recorded. If any objections, write in the chat. If no objections, I am introducing the speaker again. Sorry for having to repeat it. So our guests today are Aram Arutyunov and Sergei Zhukovskiy from Moscow. And they are experts in variational analysis, well known internationally. And we are actually in our webinar returning to the sources, to actually variational analysis and classical stuff like inverse and implicit functions. And Aram and Sergei are among the well-known experts in this area. And not only in this area, they've been working in optimization for many, many years. I think I haven't seen Aram for more than 20 years live. So good to see you again, more probably. So good to see you again. And the floor is yours. Teach us about inverse and implicit functions, please.
Thank you. Today we shall tell you about local and global inverse function and implicit function theorems. I will start and Sergei will continue. The first part of our talk is about abnormal case. Let's X and Y capital be Banach spaces, C be a topological space without any additional assumptions. And F is mapping from this product to Banach space Y capital. Let's consider this equation 1 with unknown X and a parameter sigma belongs to sigma capital. The classical implicit function theorem states that if F is sufficiently smooth, and this equation holds for certain x0 sigma 0 fixed, and the normality condition holds at the point x0, it is a well-known condition that linear mapping, which is equal to the first derivative at this point, is surjective linear operator. Then there exists a neighborhood O capital of the point sigma 0 in a continuous mapping such that this equation holds and G of sigma 0 is equal to x0. It is well-known theorem which everybody knows and apply in different areas. Let's consider the following two questions. If the normality assumption, fails, then under what condition does there exist an implicit function G? The second question, under what conditions there exists an implicit function G defined not on a certain neighborhood, but on the whole space sigma? We will start with the first question, and I will tell you about first question, and Sergei Zhukovskiy will tell you about the second problem. I want to formulate the main result of the first part of our talk, and okay. Let's repeat. X0 be Banach space, sigma topological space, K capital be given closed convex cone and phi as mapping phi as above. We consider the following equation. 2. Here appears one more restriction: x belongs to k, with the unknown x and the parameter sigma belongs to sigma. For simplicity, you can omit this restriction. You can assume that k is equal to whole space x capital for simplicity. Also, you can additionally assume that all spaces are finite dimensional. The result, which will be formulated below, is considerable in this simple case. But this restriction, which I wrote here, is presented here, is very important for different applications. For example, in mathematical programming problems, in optimization, in mathematical economics models, and so on. So let's continue. Let's x0 sigma 0 be given, and this equality take place. If f is sufficiently smooth, the function is sufficiently smooth, and Robinson normality assumption take place, then the Robinson stability theorem implies that there exists a neighborhood of O capital of sigma 0 such that for any sigma belongs to this neighborhood, there exists such G of sigma belongs to K such that these all conditions for are satisfied. The first condition shows us that it is implicit function. The second gives us linear estimate for this implicit function. This result is well known and was obtained by Robinson. Moreover, if it can be proved additionally that the function g can be chosen to be continuous. So it is a version of classical implicit function theorem for when we have this convex cone, closed cone. If this convex cone is equal to all space x capital, then we get the previous maybe more classical theorem. Let us turn to implicit function theorem without a priori assumption of Robinson's conditions. This is Robinson condition, I repeat. We shall assume that the following assumptions, smooth assumptions for function f are satisfied. The first, in neighborhood of this given point, the mapping f is twice continuously differentiable in x uniformly in sigma. For each sigma, the mapping, this mapping, whose values are symmetric Billian mappings, satisfy the Lipschitz condition in x, and the Lipschitz constant does not depend on sigma in some neighborhood of sigma 0. The next one, all these mappings are continuous in some neighborhood of sigma 0. Let's introduce one more convex cone. this cone is a sum of closed convex cone K and one-dimensional subspace span of given point x0, and put C capital is image of this cone by linear mapping, which is described by a derivative, first derivative of f due to x. We shall assume, so we introduced two cones, K and C capital. We shall assume that the following assumptions hold. Linear hull of cone C capital is closed and topologically complemented. Of course, in finite dimensional space, this assumption is automatically take place. If we have Hilbert space, then we have topologically complemented is also automatically fulfilled. But span, of course, can be not closed. But we assume that this assumption take place. Let denote by P a continuous linear operator, any continuous linear operator that projects Y capital onto a topological complement of span C, of linear hull of C. Of course, if Y capital is Hilbert space, we can take P by P the orthogonal projection of the orthogonal projection. Okay, and now let's see the main definitions. The first, let H, any vector, belongs to this cone K, which satisfies this equation. H belongs to kernel of linear operator, this linear operator. The first condition, the second condition, and the third condition. We have this quadratic form, second derivative of f due to x, and we put here this vector h. It put here minus, and it must belong to cone C capital. We say that mapping F is said to be too regular at given point with respect to cone K capital in the direction H, this direction, if the following condition take place. Let's discuss about this assumption 6. Here are sum of two convex sets. The first is image of cone K by a linear operator of the first derivative. The second one, here is also linear operator because H is fixed, and the second one is we put here any vector belongs to this intersection of cone K and kernel of this linear operator. It is convex cone, and so this one is also convex cone. So, and the first one, the first term also is a convex cone. So we assume that the sum of these both of these convex cone is equal to the whole space Y. If it holds, then we say that mapping F is to regular at given point with respect to K in the direction H. Okay. For example, if Robinson's regularity condition holds, then we can take H equal to 0. Then the first term will be equal to 0, and the first cone will be equal to Y capital. It is Robinson's regularity condition, assumption condition. Okay, it is a trivial particular case. Of course, this assumption can take place also if the first derivative, this derivative, will be is equal to 0. Then Robinson's condition we cannot use, but this condition can take place. Okay, now the main theorem. The main theorem. Let this interior be non-empty, and assume that there exists any vector H such that the mapping F is to regular at given point with respect to K in the direction H. Then, if such a vector exists, then for each vector L belongs to this cone, there exists a neighborhood O of the point sigma 0, delta positive, C positive, and a continuous mapping G, which maps 0 to cone K, such that the first, it is implicit function. This equation holds for each sigma. And the second, this estimate take place. Here are 4 terms. The first one, second one, this term, and the fourth term. Please, for your attention, here is square. It is very important for abnormal case in all estimations. Okay, now I shall describe what does mean these terms and this term C delta. These terms are defined here. The first one, this formula, the second one, and C delta is a cone hull of this intersection, neighborhood of vector L and linear hull of C. Yes, and cone denotes the conical hull of this neighborhood. Okay, so once more, we here defined this first term, the second term, and this cone C delta. Once more, I will come back and show you this estimation. So this a priori estimation holds. And very important that here is square. We can now omit this square because there are counterexamples which shows Yes, there are counterexamples which shows that we cannot omit any term, this one, this one, this one, and cannot omit here square. Okay. Under the additional assumption that this cone is linear subspace, in the estimate 8, the second term can be omitted, but only if this image is linear subspace. Once more, I will return. Yes, this term can be omitted. The next. If we have now this restriction, which is described by cone a K capital, in other words, K capital is equal to whole X, and all assumptions of theorem hold, then there exists a neighborhood O of the point sigma 0, constant C positive, and a continuous mapping such that it is implicit function theorem. 7 means that it is implicit function theorem, and this more simple estimate holds. We here omitted both first and second terms, and this term take a very simple view. It becomes very simple. Of course, a classical implicit function theorem follows from this corollary. Now, Сереж, как будет относительная внутренность?
Relative interior.
Как?
Relative interior.
Relative, yes, I forgot.
Relative.
Relative. Sorry, I forgot this word. So, theorem 1 is valid only under the assumption of non-impedance of the cone of this real interior. However, if the space Y capital is infinite dimensional, then the relative interior of the convex cone C can be empty. For example, in space L2, the positive non-negative cone has empty relative interior. It's well known. For example, let's present an implicit function theorem which is valid without the a priori assumption that this relative interior is non-empty. Let the mapping F be two regular at the given point with respect to this cone K in the direction H. So there exists this direction. Then, once more, there exists a neighborhood of the point, given point C positive, and a continuous mapping G, such that G is implicit function, and this estimate holds. This estimate holds. This theorem is true without additional assumption of that relative interior is non-empty. But this estimate is more worse than previous estimate because we don't assume that relative interior is non-empty. Of course, once more, please see that here it must be put, we have a square. Only without this square, it is also wrong. This result doesn't take place. Okay, so I finished with the first part, which was devoted to abnormal case. And now Sergei Zhukovskiy will continue with global theorems, inverse function theorems. Thank you. Sergei will continue. Please.
Thank you, Aram.
Hello. I'll continue with the second question that was mentioned in the introduction. Can you see my screen?
Yes.
Okay. So, as before, X and Y are Banach spaces, sigma is a topological spaces, F is a given mapping, and we consider equation 1 with where sigma is a parameter and X is the unknown variable. We will say that function G defined on the entire space sigma is the global implicit function if it satisfies this identity. Let me recall a classical result concerning global implicit and inverse functions, namely the Hadamard's theorem. This assertion states that if we consider finite dimension spaces X and Y, and the spaces coincide, and the continuously differentiable mapping F from X to Y, which satisfies the uniform regularity condition, namely for every X, the derivative at point X is invertible, and the norm of this, of the inverse of this derivative is bounded on the space X. Then this mapping F is a diffeomorphism. Now let us again consider finite dimensional spaces, but assume that the dimension of Y is less than the dimension of X. In this case, of course, a continuously differentiable mapping F cannot be a diffeomorphism, cannot be a homeomorphism. But still, it can have some useful and good properties. For example, it can have continuous right inverse mapping. So it is natural to consider the question under which condition this right inverse exists. In order to state main result of this part of the talk, let me introduce the following notation. Capital L states for space of linear bounded operators from X to Y. SL stands for the set of all surjective operators. B stands for closed ball. And one more notation, cov A. This function cov A, this notation cov A denotes the covering constant of linear operator A. Namely, we take the image of the unit ball and consider the largest number alpha such that alpha neighborhood of 0 is a subset of the image of unit ball. And Banach open mapping theorem, its equivalent formulation, states that this number, this covering constant, is positive if and only if this operator is surjective. Now for nonlinear mapping F, define the following function. First of all, we take an arbitrary continuous function phi and consider the function alpha defined by the equality on the screen. We take every x from T neighborhood of phi of sigma, every sigma, and take the smallest covering constant of all these linear operators, first derivatives of f at points x. And now we can formulate the global implicit function theorem. Assume that x and y are Hilbert spaces, and the f is smooth enough. The smoothness conditions are on the screen. Take arbitrary continuous function phi, and assume that either this integral equals infinity, or this inequality holds. If this assumption holds, then there exists a continuous global implicit function satisfying this estimate with integral. Let us consider now, let's say, a simplification of this result. This regularity condition at 11 looks maybe a little complicated. So assume that the covering constant of all the derivatives is bounded from below by a positive number a. Then this estimate 12 takes the following form. The distance from the implicit function g to given initial function phi does not exceed the value of the given mapping f divided by this constant a. Below we consider one more global implicit function theorem for Banach spaces. And we will use assumption 13 instead of these more complicated assumptions with integrals. Okay, now x and y are Banach spaces, and we assume that in the topological space sigma there is a function pi, which is continuous and non-negative. We define these sets sigma of d, which are Lebesgue sets of the function pi, and assume again that f, the mapping f, which defines the equation, is sufficiently smooth. Here there are three conditions, A1, A2, and A3. For example, if we additionally assume that the spaces x and y are finite dimensional, then these three assumptions are equivalent to continuous differentiability of f in the variable x uniformly with respect to the pair x sigma. And in Banach space, this assumptions has this form. Okay, now assume that this constant a is positive. Then for every continuous function phi, for every positive number gamma less than a, there exists a continuous function g, which is a global implicit function, and this function g satisfies this estimate. as before, we can replace this assumption 14 with some weaker but more complicated assumption with integrals. In fact, we can replace it by this assumption 11. And the assertion remains correct. But yes, I want also to note that theorem 4, as well as the previous theorem 3, they both generalize Hadamard theorem. Hadamard theorem follows from these results. And I think that it is important to know that these estimates are useful and important. So let us consider the applications of this estimate. But first, I'll state a corollary of the second global implicit function theorem for the inverse function problem. Let capital F be a continuously differentiable mapping whose derivative is bounded on every bounded subset of X, and it is bounded uniformly. And again, this constant A, the smallest covering constant of all the first derivatives of the mapping F, is positive. Then, for every continuous function phi, and for every positive gamma less than A, there exists a continuous invert function capital G, satisfying this estimate. Simple examples show that we cannot replace the word continuous in this assertion by continuously differentiable or just differentiable. Even if capital F is a linear operator, then there may exist no smooth or Lipschitz inverse function, but continuous function, inverse function exists. Okay, and now let us discuss a little the application of the second global implicit function theorem to the following problem. We have a subset, a closed subset C of the topological space sigma, and a continuous function phi, which is defined on the subset C, and this function phi is implicit function. And there arises a question, can we extend the function phi, preserving the properties of continuity and the property of a function to be an implicit function? And the answer is affirmative if the assumption of, under assumptions of global implicit function theorems. Namely, the following result is valid. Assume that the topological space sigma is Hausdorff and paracompact, and the mapping F satisfies assumption A1, A2, and A3, and uniform regularity assumption 14. Then for every closed subset C and every continuous function phi, which is implicit function, there exists a continuous function G such that it is an extension, continuation of function phi, and this function G is implicit. Let us briefly discuss the proof of this theorem. Let us deduce it from theorem 4. Okay, since the topological space sigma is paracompact and Hausdorff, then Michael's selection theorem implies that this continuous function phi can be extended to the entire space sigma. Let us now apply theorem 4 to the extension of the function phi. Here is theorem 4. By theorem 4, there exists a continuous implicit function satisfying this inequality in 15. Let us take a point sigma from the set C. Since phi is an implicit function on the set C, then the right-hand side of this inequality equals 0. And therefore, G coincides with phi, the value of function G coincides with the value of function phi. And so G is the extension, continuation of function phi. Now, okay, I want also to mention that all these results, namely global implicit and inverse function theorems and theorem on the continuous extension, they are remains new if the spaces x and y are finite dimensional. So the results of this talk, of the first part of the talk, were published in the papers 1 and 2, which you can see on the screen. And the results of the second part of the talk about global implicit function theorem are partially published in the paper 3. For the case when the spaces x and y are finite dimensional and the mapping capital F is Lipschitz continuous, the global implicit function theorem was obtained in the paper 4, joined with Professor Ismailov. Well, basically, that's all the results I wanted to talk about. Thank you for your attention.
Thank you, Sergey. Thank you, Aram. A nice presentation and good timing, by the way. So we have plenty of time for questions. And do we have questions, please? The audience? Okay, while the others are thinking, let me ask you a very short, naive question. What makes you think in this direction, to consider directional regularity? What's the motivation for going in this direction?
Is this question about first part of the talk or the second part?
You choose.
Okay.
I can ask myself. For me, it is interesting. It's the main goal.
Now, this is a great motivation, by the way. This is what motivates all of us mostly. Any more motivations apart from this one?
Well, I can add a little. There are some papers which were not mentioned in this talk, where, I mean, they don't belong to us, but similar results are used for the investigation of differential equations and the application of such global implicit inverse function theorems lead to some assertion on solvability of certain differential equations. But we did not study applications.
Okay,
Of course,
thank you,
sorry,
Aram.
I want to add. Of course, there are a lot of applications of this. There are already applications of these results, and will appear new applications. But for me, I told the motivation was only the interest.
Okay, thank you. I have a feeling that this is actually becoming a hot topic. The whole, of course, topic of regularity, covering, etc. After Robinson formulated all those things in the 80s. Now more and more people are moving into this area, and there are important applications apart from just interest. And in recent years, I've noticed that many people, or maybe some people, not many, are looking for directional versions of various regularity concepts. And they claim to have significant motivations for that. I'm not an expert in this area, and I want to believe them. And of course, just having interest, it's also a strong motivation. So this was a little bit of warming up discussion, and I'm hoping that now we have some more specific questions from the audience. Please.
Yeah, if nobody else wants.
Janusz,
So
please.
the trick with the phi was very nice. When you did this extension, because I mean, it follows in such a natural way, and actually it's a pretty difficult question at first sight whether you can extend a solution with this a function that is a solution of the equation. That at first sight totally non-trivial, and then with this phi trick, you find a very elegant solution to that. Are there other tricks of that kind you can play with that phi? Because this looks like a very versatile thing that you could use in a range of situations if you know how to. And I don't.
Well, this is our main trick with phi. In fact, yes, we think that there should be some other application of this estimate, and maybe in future research will but I can provide one more application which uses this estimate. For example, if we consider a function, let me. Okay, here is the main equation, and assume that in the right-hand side there is okay, and assume that we have a function phi and substitute it to equation 1, and this function phi is almost implicit function, namely the value of the composition of f and phi is uniformly bounded by some small number. Then by this estimate, it follows that there exists a function g, which is implicit function, and which is close to this function phi. Well, it is not even an application; it is an interpretation of this inequality. But still, I think that it is a little interesting.
Yeah, that reminds me of something I've once seen in ordinary differential equation solvers, some theory behind that, but it's not exactly that. It's a bit like inexact implicit function theorem or something of that kind. But nicer. I think this is a lot nicer than what I've seen. What this also reminds me of is like bifurcation theory. If you, for example, have a Hopf bifurcation or something of that kind, then you have suddenly something functioning like a function like spinning off That may be a good framework to formulate such things, but I'm not sure about that. Have you looked into such things?
Well, I cannot comment about bifurcation theory. Maybe it is, well, I don't have comments.
No, it's fine, it's fine. Okay, thanks.
Thank you.
Thank you. So I suspect that there may be more questions, but while I still remember, I'm forgetting things. I still remember. May I ask you if you can share your slides for our website, if you don't mind? No, not right now, in principle. Okay.
Yes.
So, do we have questions? I see a few unmuted microphones. So, do you want to ask something?
Sasha, I want to add something about abnormal properties. Very
Yes, please.
important particular case of abnormal mapping is quadratic mapping. And quadratic mappings is very important. Investigation of this mapping is very important also for algebraic geometry and for applications of automatically control. And some results about this, about stability of images of quadratic mappings, Sergey and me obtained some years ago, and you can find it in journal, Russian journal Математический сборник, сборник of mathematics.
I think it is translated as
yes,
Soviet mathematics or something under a different name. Yeah. No, it doesn't matter. We can find.
I think сборник of mathematics.
Okay.
About 4 years ago, but you can find it by our names.
Yeah, of course. Now everything is easy. The more we are in isolation, the easier many things become, actually. Just one more comment, if I can. Of course, it's a nice observation, which is followed by many people, that many regularity assumptions can be weakened by considering them not on the whole space, but on cones, for instance, like you do. And it is indeed sufficient for many applications. This has already been shown by many people. But from the point of view of interest, my interest, for instance, I'm thinking, why specifically cones? And is it really important to have linearity to go along directions? I think that there should be, there might be a way of working actually along the same lines, but without directions. This is just a comment. I don't expect you to respond to this.
Sasha, I can answer you. This results when instead of cone K, you can take any closed convex set, was extended by Sergey some years ago.
Okay, good. But I suppose you still work with directions. If it is a convex set, you are assuming that there are directions going into the point in question. But what if the space is metric? No linearity. Provocative question. I know. No. But it's beautiful. More questions from the audience? We still have some time. Please.
Space is metric. What is then the differential?
There are plenty of questions here, but in fact, differentiability in some aspects can be relaxed. People deal with metric regularity without talking about differentiability, and discovering openness, they can be defined without differentiability, maybe not in this particular context, but it is not impossible.
Yes, and one of the direction of these investigations are problem of coincidence points. This problem is stated and partially solved in any metric space. If it is equal to solve equation, it is another problem, but very close to this one. If it would be interesting for you, we can tell you about coincidence points in future in partially ordered spaces and in metric spaces.
Okay, sounds good to me. So I'm asking for the last time. More questions? If no questions, let's thank both speakers at our today's seminar for their great job, and not just by presenting at our seminar. It's good to know that people keep doing good mathematics in Moscow, for example, and also that people can do good things because it is interesting. This motivation doesn't normally work in Western countries, so it's great that there are places where it is still possible. So we do expect you to continue your presentations at our seminar. We're going to make a pause for Christmas and for New Year break, and we will resume in the beginning of February. We're going to have one more presentation next week, and after that it will be a big break. Okay, so thank you everybody, and if we don't meet, Happy New Year. Otherwise, see all of you, or some of you, next week. Thank you.
Thank you.
Yes, you then.
I stop recording.